Hi everybody, my name is Kyle, and today I'm going to be talking about declarative caching with Postgres and Redis. So just a little bit about myself. I am the head of developer advocacy at Redis Labs. We are the home of Redis, and I've been using Redis for a very long time, since about 2012. You can find me at these social profiles, Twitter and at GitHub. What I really want to talk to you about is databases. And databases are really near and dear to my heart. I've been using databases since I was a little kid. My first database was DBase 3, and then I graduated in DBase 3 Plus. And I've spent a lot of my youth on databases, learning about them and that sort of thing. Now, I wish I rode my bicycle more as a kid, but it got me where I am today. So I'm okay with that. Now, let's talk a little bit about Redis. Redis is an in-memory open source database, and we're here for high performance operational analytical or hybrid use cases. What it is really, we're from the key value family of databases, and we're really fast because we're natively in memory. Now, a little bit more about Redis. What does it stand for? This is the question we get a lot. Actually, it stands for Remote Dictionary Server. Kind of. We recently turned 10, and when I was talking to Salvatore Sanfilippo, the creator of Redis, as part of that anniversary celebration, he disclosed to me that maybe that's actually not the case. The big thing that he was looking for when he named Redis was a 5-letter domain name, and he found that at Redis.io. And to this day, that's one of the best places to go and find out more about Redis. It's a great place that has all the documentation and the performance characteristics that you would, for each command that you have in Redis, that you would be interested in. If you can't find anything in the documentation, go ahead and look at the GitHub repo for Redis itself. Redis is written purely in C, so it's completely compiled, but it's a very clean C and it's very easy to read. It's great to be able to kind of read and figure out what's going on internally. A lot of times you look at the source code of a database and it's just bewildering, but Redis is pretty friendly in that way. It's the leading in-memory database platform. We've been voted, the most loved database years in a row, and it's one of those databases that you see in every kind of role across any type of infrastructure these days. So shifting gears a little bit, what is Redis Enterprise? Now, Redis Enterprise is the commercial offering of Redis, and it offers some kind of unique characteristics and features that are not available in open source, primarily along the lines of operations. But what it really does is makes Redis an in-memory multi-model database. So it really enhances Redis in a lot of ways in regards to both how you would use it and how you'd operate it. But really, at its heart, you're always interacting with open source Redis. Now, if you're a large organization and you, by that function of being a large organization, you use a lot of Redis, Redis Enterprise makes running Redis really simple. If you're a small organization and by nature of, say, your product, you are somebody who uses a lot of Redis, that'll work for you as well. But certainly, you can go and install Redis open source on your laptop or even a small production use case, and it's totally fine. So let's move on and talk about caching, which is one of the leading use cases of Redis. Not the only one, but one of the leading ones. This kind of comes into play because there's a natural alignment between how applications start. They usually start with something simple like a single box, single VM, or a single container, something along those lines, connected to something similarly sized for the database. And almost any application is going to have something along this when it starts. It's going to be pretty simple. Now, there is a differential here. Databases are complex things generally, and the applications you build are comparatively less complex. So what happens is you start pushing a lot of traffic because your application or service gets really popular. When you do so, what happens is your little box here is sending all this information to the database, and the database can quickly get overloaded because it's actually doing a lot more sophisticated things. And how do you solve this? Well, one of the common patterns is to use caching, and Redis is used in this way very frequently. So basically, you're still doing all your writes to the database, and then a lot of your reads are going through a cache. In this case, a percentage of those reads are going through the cache, relieving more capacity in your database for continued scaling or for continued performance. So let's take a look at that performance bit. How does it actually work? Now, the way you get data into a cache is you do a population or a repopulation step. So you can take a query that takes a long time, say 100 milliseconds, and you push it into the cache, and then subsequently, your application server is going to read from the cache instead of reading from the database. And that's going to take a much smaller amount of time because what you're actually doing with the cache is usually much lower complexity. You're not having to sort things, it's already pre-sorted. You're not having to retrieve things across a spinning disk, perhaps. So, you can get from 100 milliseconds down to a millisecond pretty easily. In addition, you might have situations where you're doing it very less frequently. So you may have that 100 millisecond ones that you're repopulating every, say, 60 seconds. If it's needed, if it's older than 60 seconds, Redis will get rid of it. Now, the other thing that you're doing here is you're really saving performance. But the other thing that it can do is help with load and scale. Now, in this case, let's say you have a database that's really running hot with 10,000 queries per second, and that gives you a 95% CPU load. That's hard to deal with. What are your options here? Well, one of the options people do is they try to scale out their database. That can be hard. It can be expensive, or sometimes it can be impossible. So in that case, what you really have to do is think about other solutions. And one of those other solutions is putting a cache between your database and the application. In this scenario, basically what you're doing is you're saying, 90% of the reads that you're doing from the database are going to go through the cache. And that can really help you a lot as far as the load on your CPU. So you can continue to handle more traffic, say, with the same hardware by the same database hardware and database licenses by just having that cache in the middle. Now, you think, well, hey, why don't I just cache everything? Well, that's not a great idea either. So in this case, you have something that is running from your database directly to your application server in 1 millisecond, and you have 2% CPU load on that database. It's already fast. I can't help you there, right? Like, this is something that you really have to consider. If it's fast enough, don't cache it, right? And I'll tell you why. In this case, adding a caching step in can cause some problems. So here you have a repopulation hop, and that's one of those things where you're taking, and maybe it's a millisecond at the database, and you're not under any particular load. And in that case, you're populating into the cache at 1 millisecond, and you're getting out of the cache at about 1 millisecond. You're trying to make things faster, but actually you end up making it slower because you're increasing the latency by adding extra hops when you're having to repopulate the cache. So these sort of things mean that you can't just cache everything. You can't just cache it at the library level. Now, the other thing to look at is, should certain things be even cached? That's something to really consider. So think of this. This is a massively simplified example of a login password entry situation. So you cache, you're pulling the password that's hashed out, and then you're taking the user's hashed password and comparing those. This particular piece of the cache, this key, is only being refreshed every 60 seconds. Okay, that seems reasonable for the most part. But what happens when someone changes their password and then it's written to the new database? Now, under most scenarios, this may not be synchronously updated to the cache, and that can be a big problem. So let's say before the 60 seconds is over, somebody tries to log out and then immediately log back in. 15 seconds. That's human scale. The user comes in, puts their username and password in. They just changed, and it then refers to the cache, and that's not correct. And it says, hey, that password doesn't match, and somebody is cursing quite a bit in that process. So this is an example of something that you probably should never have hashed, or you should have some extra strategy involved, so you're making sure you're always updating things in the correct way. So it gets complicated. Another thing to look at too is when you have situations where you're caching a lot of values over and over and over again, and you're filling your cache up with things that are not very relevant to cache. In this case, we're sequentially going through something. And that's probably not going to happen for a while. Let's say that you're sequentially going through the user IDs and you're caching everything here. Well, there's probably more valuable things that you can put in your cache. And because caches are usually smaller than the data that they're being referred back to, this can cause a lot of problems because you really don't have that decision point which is more important in a given query, one or the other. So talk about some of the problems, maybe why you should or shouldn't do it. Now let's talk about what it looks like when you do caching, right? This is a pretty typical pseudocode example. You have your query, very simple query. You'll take that query text and you'll hash it, right? This is going to become an identifier or a key for that query. Now, if it exists in Redis, you'll take the key and say, does this exist here? If it doesn't exist, we're going to go ahead and do repopulation step. So we're going to go out to the other database and we're going to query it with the query that we had before. We're going to turn that data back to the application. That application then will take the key that we generated above and then the data there and set it into Redis. And so at that point now it resides in Redis. And then we're going to set an expiry on that key. So in this case, we're going to say expire in 60 seconds, in a minute. So that's if it didn't exist. If it does exist, we're just going to jump ahead here. And if after that already happens, we're going to do a Redis get here, and we're going to get the key out of it. And as you can see, when we get the key out, so we're always directly reading from Redis. Now, if we take a look at a pseudocode example, you're maybe doing some testing and monkeying with things, seeing if this is really helping the overall performance. You could do something like commenting out the part about getting things from the cache. And you can see this is pretty typical, right? I think it has a lot of problems, and let me tell you why. If you take a look at this, it adds a ton of boilerplate. It really has hard to understand code. You have a surface area for bugs. You're tightly coupling a bunch of stuff, and in the real world, it's going to get a lot more complicated. So let's take each one of these problems in turn. Here, what we're doing is we're actually adding in useless lines of code by commenting things out. Comments like this tend to be sticky in your code base. They're really doing nothing, and they're actually just making things harder to understand because like maybe a junior staff member might come in and say, I don't know why that's there. Did it not work? Is it something that we can safely delete? And so it really has some kind of code quality concerns to it. And then you actually introduce a surface area for bugs here. Now I made a small change. I don't know if you caught it. Do you know why? Well, what's happening here is I made a mistake. I'm actually using the key that I'm generating from the hash and sending it to the database, which is not going to work. Why is it not going to work? And it's because it's not the right thing. We should use it in a query instead. Even worse is something like this, where we have a query and we're sending this and we're using Redis get key. This is a problem because this might actually work sometimes, and I'll tell you why. So in this scenario, this might work for a while and then cease working, which is the worst type of bug. What I'm doing here is maybe I had a previous iteration of the script where I have populated the cache and then I'm getting the value from it. So this is a problem. It's not going to give you the results back that you want after the key has expired from the database. So you can see here, we're still checking Redis, but we actually never set it, right? So this should really be Redis, this should not be Redis get, it should be DB query here. Then we talk about tight coupling. This is something that's interesting and it shouldn't be overlooked. Really, there's a situation here where we have a problem with the tight coupling of a couple different things together. So this is going to occur over and over and over again in your code. This is boilerplate functionally. If you change your Redis client, you're going to have a ton of code to change, which is not great. So that's something to keep in mind too, but also maybe you're going to change your database client. These things change at a higher frequency than you might imagine. Over the course of a piece of code that lasts several years, this might go through several iterations, whether it be versions or whatever. And for example, in Redis, we're changing our protocol. So we expect the changes to occur in the clients as well. So you have the tight coupling. The other thing I want to touch on here, I don't really have a slide for it, is that in the real world, this is going to get a lot more complicated than what I've outlined. It's a very simplistic pseudocode example. You start bringing in, asynchronous code, and you try to start thinking about fallbacks if Redis is not available or if the database is not available. The boilerplate will increase significantly. So effectively, what this comes down to is you have imperative caching here, and maybe what we want is declarative caching. So let's go through some definitions here. Imperative is this idea that you're going to say what and how to do something. So think of this as tying your shoes. If you've ever seen the explanations for tying your shoes, they are about a page long. No wonder it takes kids a while to learn this stuff. Declarative, on the other hand, has a different approach. You say what, but not how. So in that case, what you're doing is just saying tie your shoes. Now, how does this look in code? And in code, imperative is basically if then else statements, for loops. These are the basic fundamentals. There's nothing wrong with this, but in an repeating over and over pattern, it gets a little bit problematic. Now, it's a bit like a recipe, right? You take a look at a recipe, it's going to tell you exactly how to make some food. And we'll return to that in just a moment. Let's look at declarative and how it looks in programming languages. SQL itself is a declarative language. Redis is based on commands, which are declarative. And even HTML is declarative. In HTML, you don't specify exactly how you want the button. You just say button, and then maybe you define a style somewhere else, which is also declarative. Um, but if you think about this in the contrast to recipes being how to cook something, declarative is like a drive-through window. You just go up to a drive-through window and say, I want a cheeseburger. You don't tell them how to make a cheeseburger. So it's an important difference. Now, taking a look at imperative code, this is nothing wrong with any of this, but as you start building complexity in your application, it becomes a problem. So let's contrast this with declarative caching and where this comes from. So why would you do this? Well, SQL is in itself declarative, as is Redis and a lot of other things that we run into. Um, and so we can try to integrate the cache control with the query in declarative caching, which is kind of an interesting step. The original idea for this is Gaius. He's the author of Slownik, which is a Postgres client for node.js. And he has this concept called interceptors. And I like to think of them almost as like middleware. And it's going to basically go in and intercept certain parts of it and then be able to perform actions on it before it even gets to the database. Now, the Redis implementation was written by me. You can find it this. I'll have this URL at the end of the presentation as well. But really, this is an interesting idea. So your whole thing is the caching then occurs in with the query instead of having to have all that boilerplate. Let's take a look at how that looks. So imperative, here's our little code snippet that we've used over and over again. Nothing special to this. Here's how it looks. The same thing basically being done in a declarative way. If you notice, there's a big difference in size, and also it doesn't look nearly as complex. And it's going to be easier to modify and maintain as well. Let's dive into it. The actual SQL, the actually code here that you're looking at that's kind of special is this line here. Now, if you haven't used JavaScript very frequently recently with very modern implementations, you have this ability to do tags on different types of strings, and I'll tell the database, or excuse me, the application, how to manage it a little bit. So this is just something to add into it that's required by Slownik. Now, if we take a look here, this is actually the relevant part. So in this part, we are actually telling the caching engine embedded into the client how to manage this. So we have dash dash indicating a SQL comment, and then we have the special at cache TTL60. So this just is how we're articulating, yes, cache this for 60 seconds. And then here's just the normal SQL query. So that can be anything. And of course, you can do the normal things like interpolate values or anything like that. So from the Redis side, what are we doing? Basically, we're taking this, we're interpreting that value at the client library level, and then we're performing a Redis operation from the client. We're going to use the command setex, which is set with expiry. We have a prefix, and we've hashed the query just as we were doing in the imperative version, and then we're setting 60 seconds. We're setting the results. So that's when we fill the cache. When we are getting a situation where we want to fetch from the cache, we basically run a get command, which is very similar to the set command without all the arguments. One thing to keep in mind is that this is particularly, it will make a differentiation between how long you set the cache for. So you can end up with situations where you have multiple copies of the same result set, but just being cached for various lengths of time. So that's something that's a little bit hard. Now I'm going to run a demo. Well, I'm going to show you a demo. It's a load generator, basically where we're pushing a Postgres table that has, basically user type information, email, username, when it was created, user ID, using an insert. It's happening, every 50 milliseconds, 20 times a second. And then we have the demo itself. It's a hard kind of query. It is where we're doing a count over a regular expression, and we're caching that for 10 seconds. Now, I will tell you that this is going to happen every 50 milliseconds, and I had some problems recording the screen and also doing this. So this is pre-recorded, but you can get similar values. You can try it out on your own. So take a look here. Basically what we're doing, we have a situation where we're going to go ahead and start the actual thing on top and then the population step down below. So that's that's adding information to Postgres. Now we're doing this without any caching, so we're getting values back with an average time, the number of queries across the number of queries of about 16 milliseconds response time, and it's going to stabilize a little bit into the 16 millisecond range. Now I'm going to go ahead here and add in the caching. So I'll run this. You can see here, here's the caching, okay, and then I'll populate as well while it's going on. Okay, so you're already seeing an increase in time, and it'll trend down because there was some repopulation step that took and connection step that took a little bit longer. So here we're down to 4 milliseconds from 16, right? And despite we're running this, now I do want to point out that the email count is not going up every single time because that's caching, right? So we're holding that at 2162 for a while, and you can see here now it just changed to 2291. So we're still in the 4 millisecond range, even though the values have gone up significantly. So it really provides a lot of performance without a big change. It was just that simple step there. So if we take a look at what this will do, there is some things to consider. There are limits here. One of this is a cache aside, technically. You could think of it maybe as a read-through since it happens at the client level, but we'll call it cache aside for right now. This is only one of the many caching patterns that are available. Redis supports several of these, including right behind with one of our new products called Redis Gears, where we can actually execute scripts, Python scripts inside of Redis itself. Really cool technology. And we're using Redis as a blob, which is the most basic way you can use Redis, right? There is certainly a deserialization and reserialization overhead, and we're not using anything sophisticated in Redis. Redis has this whole series of data structures and modules that you plug in that can enable it to be all sorts of different things, like a search engine or a graph database. We're just using plain Jane 2 commands. So it's really not using Redis to its greatest extent. It's sensitive to a couple different things. Similar queries will cause it to do things. So I'm not really providing any control there, but you can integrate that in if you were very careful about how you put that comment in your SQL query. And of course, the cache GTL differences can come into it. So if you had another part of your application doing this at a 12 millisecond, or excuse me, a second interval, that would be duplicating data in your cache, which isn't great, but this is something that you can really manage. Now, this is a pattern that's pretty much exclusively to Postgres and Node.js only at the time. Now I'm working currently on the MySQL version, which maybe will be out by the time you see this. And using the same pattern and the same type of thing where basically what we're doing is we're just intercepting the query and then we're doing that before it gets to the database. So cool stuff there. But right now it's Node.js only. It has good support for proxy, objects, and reflection, but we think we can do it in other languages as well. Of course, if you're using ORM, this is not a very relevant pattern, although something similar could be done, but you'd have to kind of write your own syntax for that in the ORM. So we have some time left, so I do want to go over one other thing, which is geolocal caching. This is something that's really interesting. Now, one of the things that most people don't realize is that physical distances have a big impact on performance. If you take a look at the latency, if you're able to shine a light from the west coast to the east coast in a very straight line, and you could compensate for the curve of the Earth, you're talking about that proton that leaves the west coast to go to the east coast is going to take about 40 milliseconds. So this is the maximum you can go. Electrons can't go any faster than this as well. Reality, when you're sending data packets, you're going to give it close to 85 milliseconds because you're switching and you're not going in straight lines and so on and so forth. Now, 85 milliseconds doesn't sound like a lot of time, but it's an eternity. Um, if you're clicking a button and it takes more than 100 milliseconds, you perceive it as being delayed. That's human reaction time. So ideally, and we talk about this a lot at Redis Labs, is trying to get under 100 milliseconds in the complete end-to-end application response time. That's really difficult to achieve. And I'll show you a way that you can kind of cheat some things here. Now, let's zoom this in a little bit and talk about how this might work with Postgres and Redis. So let's say you have on the West Coast your Postgres primary database and the cache, and you have a user in Boston. Okay, so what's the difference here? Well, every time they do this, we're going to have a bad connection, or a bad, not going to be a bad connection, it's a bad response time, even though it is cached. Now, what's going to happen if you, say, add in your own cache on the other side of the world? That's fine, but you're going to have to repopulate from one location. So you could have a situation where you're doing multiple repopulations. So the East Coast is populating on one side and the West Coast is populating on another side, and maybe someone transfers between the two of them and they get different values. It's not going to be perfect. It's going to be pretty rough. Now, the interesting thing is that the Redis Enterprise includes a feature called active-active, and it's based on CRDTs, conflict-free replicated data types. What you're doing in that is you're actually having a way to resolve conflicts between data without intervention and at the database level. So functionally what you can do, you can have multiple geolocal servers that can be written to or read from. And if there's a conflict between those reads and writes, it's automatically resolved. So in this case, either the East Coast or the West Coast cache can basically repopulate the database. And that way you can have an up-to-date copy as soon as it can get there without any extra intervention, right? So the activity on the West Coast is populating also the cache on the East Coast, and you're connecting to whatever's closest and whatever's better. So really, active-active with Redis Enterprise helps you out a lot in the caching world. And so this is something that you do without any code. Exactly what I showed you, we just added those SQL comments and would also work here. So what are the next steps? What do you do? Well, first, grab the module. This is the case. This is the module here, or you can use npm to install it. If you want to get the demo that I showed today, go ahead and get that demo. It's on GitHub, and that'll be something you can take a look at and not take my word for it or the video that I played back for you, but you can actually see it for yourself. Follow me, of course, on Twitter, Stockholm UX, and watch me on Twitter, or excuse me, on Twitch. You can follow me on Twitter. You have to watch me on Twitch. Me and my team, we do a lot of streaming on Twitch, and you can see us all on Redis Labs Twitch page, and you can follow us individually as well if you want to stay up to track on us individually. Now, the other thing to do is subscribe to my newsletter. It's called Redis Watch, and you can subscribe to that at bit.ly Redis-Watch. It's a monthly newsletter, and this basically just sign you up for this newsletter. It's not something where we're going to spam you or anything like that. It's just for this particular relatively infrequently updated newsletter. So I'd love to see you there. Okay, at this point, I would normally ask for questions, but since this is pre-recorded, I want to thank you for your time.